Hello everyone, welcome for coming. This is the Math and Engineering Club, so yeah. Today we're going to have 4 speakers. It's going to be myself, Carlos, and 2 professors. So I'm going to start. My topic is how to use calculus, Math 181 with Chem 51 to find the pH of a pool. So let's say, let me get a mark. Let's say you're working at the gym, like a 24-hour fitness, and your boss tells you, the pool right now, it has, that's a horrible pool, but it's okay. It has 100 liters, and the pool has DI water. What DI water means, it has nothing else, it has DI water. Also, because it's chemistry and there's a lot of technicalities, you will say, well, it could react with all kind of chemicals and whatnot, so we're going to get with that after the calculus part is done. So let's say you know that the pool is always coming out because it's being filtered, because if it wouldn't be filtered, then the pool would be green and nobody wants to go in there. So you would have the rate in and the rate out. But let's say that your boss was a really nice guy, and he already got what would be 100 DI water, so it's completely pure. But you still want to have the concentration changing, because you want to mix it. So the rate of DI water going in would be the same as DI water going out, so let's just say 1 liter. So the rate going out would be equal to 1 liter. Since this uses DI water, and no concentration of anything else is being added, because later on, once we find the volume, we're going to add the concentration of a solution to change the pH of water. So for just technicalities, the concentration of a new solution being added would be 0. But if you would have some sort of concentration besides DI water, the concentration will change, but you need to find it, because you will need to find it because you don't know the rate. And well, you know the rate which is changing, but you don't know how fast it's going to get out. So what you're finding is how long would it take for the concentration of a possible chemical to change. But for technicalities, this is DI water. So let's say I would have a concentration of something, and I want to know how long would it take for that concentration to be out. Well, this is where the calculus part comes. So you have a regular equation, which is dA over dt equals the rate in minus the rate out. But you don't know what the concentration coming out is. So concentration is pounds over liters or moles over liters. So let's say you want to find the concentration. Well, the concentration would be A over C or A over V, which V would be the volume. How you find the volume, you want to get the initial volume plus the rate. So the initial volume at V naught would be what you have inside the pool, which is 100 liters. So now that you have 100 liters, you want to find the rate. But luckily, the rate in and the rate out are the same, so it's going to be 0. But you also want to get into consideration how time would affect this whole equation. So you would have to write T outside. But again, for technicalities, you already have the concentration is pure. So regardless, this ain't going to matter. But if your boss would ask you, you would use this equation, and then you wouldn't know the concentration, but then you just found what the concentration is. So you know the volume, you know the rate that's going in and out, and you know the time, because the boss is going to be, well, what about after an hour? You just plug and charge. So rewriting this whole equation again, it would give you dA over dt equals the rate in, which is 1 liter, and the concentration in, which would be 0. So it doesn't matter what it is. And then we'll give you minus the rate in, minus the rate out, times the concentration out. Which the concentration will be the formula that we just worked out. But then, since we know that there's nothing, no concentration initially, well, if there's no concentration initially, then what's the concentration going out? Nothing. So now that we know the calculus part, the only thing that would change would be the numbers that you would work. So if they would ask you, well, you started with a concentration of 5. Well, you use plug and chug. So after the calculus is done, you would have to move into the chemistry section. So the boss is like, well, find out when the pool is full. The pool would be full at 100 liters, right? So the boss would ask you, well, find the pH of the pool for someone to be able to get in. You don't want to have a low pH or high pH, get in and come out and you have like no skin on. So, I mean, it would be really nice, right? So you want to have the pH of the pool be between 7.2 and 7.4 because that's when your body can take it. So, but the DI water initially has a pH of 7. So you want to change the pH. And you have to find out, well, what about the concentration of the chemical and how much you're going to put in and how much you're going to put out. So here's where the chemistry technicalities would come in. You would say, well, what about the CO2 gas which could react with the water? Well, again, technicalities, so that would be like in an ideal situation, you would have no gas. After that, you would want to find a chemical which is not harmful for the person, but you could actually change the pH. So a strong base could work because it's used, it would go to completion, and I'll show what I mean by completion. So my choice to increase the pH from going from pH of 7 to go up to a pH of 7.3 because it's in the middle. I would pick NaOH, and AOH, yeah. Sodium hydroxide. Why? Because this is a strong base, which would increase the amount of, which would decrease the amount of hydronium inside, which would actually increase the pH. So now that I know the solution I might be using, let's say I buy a gallon of sodium hydroxide, and it tells me the molarity is 3. So it's given on the gallon that the molarity of my sodium hydroxide is 3 molars. Well, I want to know how much of sodium hydroxide I would have to add into the pool to change the pH level. So another formula that could be used to find the pH would be pH plus POH is equal 14. So we know that the pH, we want it to be between 7.2, 7.4. So you give us a range for that POH to be, which would be like around 6.8. So my goal is for the POH to be 6.8. Now what's the next step? Well, I have 2 containers. One is 100 liters, and the other one, I must say, is, it would have to be a very, very tiny amount to change the concentration, because if I would keep adding a huge amount, the pH would actually drop. So I'm gonna go with 0.00005 liters, right? So this is the amount of volume I'm going to add into a pool that has 100 liters. So see how insignificant the volume seems, but if you add, let's say, instead of 5 zeros, you would add 4 zeros, even though the volume seems insignificant, it would have a huge effect on the pH level. So once you have, now that you have the volume that you're going to be adding, you have the molarity that you're going to be adding, all you have to do is find the molarity. How do you find the molarity? Well, the molarity is moles over liters, right? So you want to find the total volume in which you would be adding to the pool. So you could divide by the molarity of sodium hydroxide. So then you could use this equation to find the pH. So we know that the concentration is 3 molars. Well, 3 molars is equal to 3 moles over 1 liter. But then I know I added this amount. So I added 0.00005 liters. Yep. Well, the liters cancel, and I'm left with the amount of moles. Since I already have the amount of moles, what I want to do is find the total volume so I could get the molarity of the pool so I could go in and actually swim. So this would give me a number, a really, really tiny number, but then again, although it looks insignificant, it would have a huge effect on the pH level. So now that I know the number would be on moles, I want to add both volumes because I want to take both into consideration. So I would get the number of moles divided by 100.000. So although this looks really tiny, again, that's a huge part. So after I get a number, I will divide the number by this huge number, and I will get another number. But this time it would be molarity. So since I already have the molarity of the sodium hydroxide, and I know that sodium hydroxide goes to completion because it's a strong base, I would know that NaOH would completely separate inside the solution, which would be the pool, into Na plus aqueous and OH. So if I have the amount that I would have here, would completely go to the amount that I have here and here. So it would not go back, the solution wouldn't react backwards. So once I find this number, I would plug it into POH. What POH means is the negative log of OH, which would be this number. But then since it completely breaks apart, I can actually take the sodium out. So then since I have this number right here, which is the molarity, I already calculated, and it will give me 6.8 for the POH. So I know that the POH is equal to 6.8. So this is the amount of hydroxide inside the solution, which will be the pool. So now that I know the POH, I can solve for pH. So let's use a really simple calculation, which would be the pH is equal to 14 minus 6.8 which will give me 7.2, which is an ideal pH for someone to be swimming. And that way I don't lose like my skin or go blind. Okay, thank you.